Hi everyone, my name is Quinn Lanners and our UAI 2023 paper is titled Variable Importance Matching. It's an almost matching exactly method for observational causal inference. So in many matching problems, we're trying to match a patients in very high dimensional spaces where they do not have identical matches. So the question is, in these high dimensional spaces, how do we determine what are the best matches? We propose matching almost exactly only on important covariates. Our method is a three-step process. We first learn a distance metric that tells us which covariates are important to match on. We then use this distance metric to create match groups, and we then use those match groups to estimate treatment effects. Importantly, our method is incredibly interpretable and facilitates auditability, and the weights can be learned in an easy to troubleshoot manner. So going back to that previous example, we would first learn weights for each covariate. Here, green indicates that covariate is important, and red indicates it's not important. So here you can see that patient 1 and patient 4 match identically on the two most important covariates and are very similar on the other two important covariates. For that reason, patient 1 and patient 4 are matched together, and it's very easy to understand why. So in our framework, we start with a data set, and we break it into a smaller training set and a larger estimation set. We use this training set to do distance metric learning, and we then use that distance metric to do nearest neighbor matching on the estimation set. We can then use those match groups to estimate causal effects. Now, our research focuses on the distance metric learning. The VIM, or variable importance matching method that we propose in this paper, builds off of the MALTS, or matching after learning to stretch method. In MALTS, we optimize an objective function of an in-sample nearest neighbor estimator to learn the covariate weights. Whereas in VIM, we use the variable importance measures of an outcome model to assign the weights. Now, the benefits of MALTS are that it's accurate to most outcome functions and requires little to no user tuning. However, the objective function is data hungry and computationally expensive, and therefore does not scale well to large and high dimensional data sets. So we made VIM adaptable to various variable importance metrics, and therefore it can be configured to scale to large and high dimensional data sets. However, it's important to note that you must choose a variable importance metric that works for your data set. In our paper, we operationalized VIM using the magnitudes of lasso models coefficients as the weights. I want to thank all my collaborators in Duke's Almost Matching Exactly lab, and I invite you to read our paper to learn more.